So we've been talking about dark matter, and now we're ready to talk about galactic rotation curves. So here's just a nice visual of, I don't remember what galaxy this is. I think perhaps M33. I'll have to check that. But you've seen a plot like this before. Basically, the Newtonian prediction is the dashed lines expected from what is observed based on the starlight and also the gas that can be determined as well. And then the observations of the galactic rotation curve, where you see there the data points with error bars. So we're going to get into the details, a little more of the details of trying to understand the quantitative aspect of this prediction and discrepancy with data. So it's, of course, not just one galaxy, it's many, many galaxies, and in particular spiral galaxies. And so what you'll see here, again, is velocity, galactic rotation curves, data with error bars, and then the various components, a disk of stars, a gas component that has a smaller contribution, and those curves that you're seeing would be the inferred velocity just based on those contributions by themselves. What seems to be required in order to have the observations agree with the underlying model is to introduce a halo of dark stuff that is not seen the way that stars and gas are observed. And this is a dark matter halo, it's called. It's the dark matter hypothesis. And this extra mass would have to have an extended distribution in order to end up with rotation curves that we see. Right, and so that's just what this text here is saying. So this is sort of the picture that you might construct in your mind for what our own galaxy and what other galaxies look like if you could see this dark halo. So there's a galaxy, a sort of galactic disk, embedded within a much larger dark matter halo, which is not perfectly spherical, of course, but at least a first approximation, that seems to be a good approximation. That's supported by a dark matter simulation. So, for example, there's this Millennium simulation, which I believe ran in 2005. There are many more simulations that have run in the mid-90s and certainly since the Millennium simulation. But one can go to this website. Whoops, if I can actually click on it, and I apparently cannot. That's okay. But what I will say is from many, many of these, they're called n-body simulations. One sort of gets at what seems to be a sort of general form for what the distribution of dark matter is, at least in a halo around, like, one more or less spherical object. It tends to be that the dark matter density has this sort of scaling. There's some sort of constant that tells you something about the dark matter density at a particular distance. R, right, is sort of the distance from the center of that identified halo. And there's some other dimensional parameters as R naught and A naught. But for example, Navarro, Frank, and White, the NFW profile is perhaps one of the most well known. And according to their simulations that they ran, they found that this form is also obeyed, but you let alpha be equal to 1, beta equal to 3, and gamma equal to 1. And they also have this parameter A and R naught equal to some number. Now it may be 20 kiloparsecs for example, a particular simulation that they did, but right, each halo is going to have a different sort of characteristic lengths associated with it.
We're going to be interested in our spiral galaxies, and let's just think about what a galaxy is. It's more or less has sort of a disc shape to it, and I'll get a picture going here, and I'll put it in sort of red because I don't know, I just want to see a red galaxy. What do you want? Circular kind of thing. So we're looking at it from sort of the top down, and then from the side, in reality, it kind of looks like it's disky, but in the middle there's sort of a bulge, and well, it's like this. And they don't pay me for my artistic talents. Okay, so we're going to be interested in knowing or having a simplified model for what the galactic rotation curve should be. That is to say, what is v as a function of r? V being the velocity of anything, of perhaps a star, solar system, piece of gas, whatever, that is at a distance from the center of the galaxy. That distance is r, and it's orbiting around with some orbital speed, in which these orbital speeds are more or less circular. And so we're interested in knowing what should v of r be theoretically, and then we can compare that to the observations. Okay, so that's what we're interested in figuring out. What is v of r? That being said, let's just talk about the physics. You've got objects that are orbiting in more or less a circle. So let's see. Number one, uniform circular motion tells you that your your orbital acceleration, it's a centripetal acceleration, and that should be simply related to v squared over r. And then the second thing is using Newtonian gravity. Whoops, I knew that was going to happen. Gravity plus the assumption of spherical symmetry. And you might think, okay, well, maybe that's not so bad nearby the bulge, but it gets kind of crappier as you go further out, and that's true. But the corrections due to the effect of deviations from spherical symmetry are not that big. So at least let's just keep this as a simplified model. What you'd expect to have is a relationship between the force of gravity, gmm over r squared, equal to ma, in other words, mv squared over r. Now what I write here, big M, as a function of r, what I mean is for this particular particle orbiting at a distance of r, it is attracted to all the mass enclosed within, this is supposed to be a circle, within a sphere of radius r. Okay, again, assuming spherical symmetry, use Newton's shell theorem, and that tells you that it feels the mass of all the mass enclosed, but nothing from the outside. Okay, that being said, the mass of whatever object you're interested in, whether it's a star or piece of gas, whatever, it cancels, and this allows you to solve for v as a function of r, and also the mass enclosed, and so that simple relationship should be this. Let's see if I can clean this up a bit. So that is the prediction for, again, assuming spherical symmetry and Newtonian gravity, what you'd expect v to do as a function of distance. All right, so what's a simplified model we can use to predict what the mass enclosed is? And for that, I'll just simply going to tell you that the observed surface brightness of a galaxy, that is to say the amount of light per unit area, I, is equal to some constant, I'll call it I naught, and then it sort of exponentially decays as you move away from the center of the galaxy, and this parameter Rs is called the scale length. And for each galaxy it's a different number, but for example Rs is approximately 4 kiloparsecs for, I believe, M31. Okay. You might think about taking this this surface brightness and or this brightness per unit area and turning this into a distribution of mass. And so a simplified assumption would be that the amount of mass is proportional to the amount of light, and therefore you would write capital sigma, the mass per unit area, as a function of r. You can think about modeling that as some constant sigma naught times e to the minus r over rs. Now, so this is a simplified model, and this is not quite right. Of course, you'd expect the ages of stars, for example, to be different nearby the center as opposed to far away, and how exactly the gas mass scales with distance is going to be different, but at least this is a place to start. If you take this at face value, then what you can do is compute the mass enclosed within that radius, and since this is a mass per unit area, then the way to compute the mass enclosed would be to integrate over all angles. So we're doing polar angles, and over all different radii out to a maximum r. And so that means that on the inside, this integration variable, I'm going to treat it as r prime. And therefore what I'm writing here is the integral, if you like, over different area elements. And then what needs to go here is the mass per unit area. Okay. I'll leave it to you as an exercise to compute this, but what you should find is that the integral over theta gives you a 2 pi. The dimensionful thing that you can stick out front is the scale length squared, and then what remains on the inside, I believe, is a factor of 1 and then minus e to the minus r over rs, and then this is multiplied by 1 plus r over rs. And just as a sanity check for myself to see if this is approximately correct, you expect that m of r, in the limit that little r goes to 0, that this should go to 0. In other words, you're not encompassing any mass. And you can tell that these terms here, when r goes to 0, you have e to the basically 0 times 1 plus 0. So you will end up with a 1 minus 0, and that gives you 0. So at least that is consistent. Now, you can use this mass, as computed here, and jam it on into this formula here to make a plot for what you'd expect V of r to be with these simplifying assumptions.
So with everything in mind, let's first talk about what kind of galactic rotation curve you'd expect to get if you just had a galactic disk that was made of baryons. And so what I'm going to do here is I'm computing the mass of baryons within a certain radius, little r. And what I'm doing here is, although this can be done analytically, I'm also showing off my Mathematica skills. Right, we're integrating over the little differential area elements, and so we've integrated over angle. That's where the 2 pi comes from, and then this piece remaining is part of the surface mass density, if you like, RP. I'm using that for r in place of r prime, and this leftover RP is part of the integration measure, and we're integrating that from 0 to r. That'll give me the mass of baryons enclosed within a a circle or disk of radius r. And then what I'm doing here is I'm plotting gm over r square rooted. That should be the velocity at a particular r. And to get the units right, I'm setting sigma naught rs and g equal to 1. So I'm doing two things here. One is I'm going to plot the predicted galactic rotation curve, and then I'm also plotting here just what you'd get if you took the entire mass of the disk and put it at a point at r equal to 0 and asked what would the velocity be as a function of r. And what you get is exactly what I said, right, the velocity in those units as a function of distance. This distance is normalized by rs, the scale length of the galaxy. But from baryons alone, you would predict this curve that sort of rises then falls off. It ends up falling off like 1 over the square root of r. And you can see there's very good agreement with that 1 over square root of r out to, starting at about about 6 scale lengths away from the galactic center. Now, we've certainly seen that this is not what the galactic rotation curves actually look like. They go up, and they don't reach their maximum and fall off like 1 over square root of r. They keep going, and they either keep growing a bit, or they sort of flatten out. And so what we'll do now is switch to a different window, perhaps, and show you what happens if you stick in a dark halo. So here I'm going to do the same thing, but now what I'm using here is a density function for a halo using that NFW profile. Right, for those parameters of alpha, beta, gamma, that was like 1, 3, and 1. But in any case, there's a density parameter, there's a scaling that kind of looks like this, and then, well, that's just what you get. And then there's some parameters you can tweak. So I'm putting in here, this was probably that parameter A. I've called it RS. It doesn't matter. But I'm going to let this, this is something that I can play around with. I can let this be equal to the scale length of the galaxy. It can be bigger. It certainly should be bigger than the scale length of the galaxy. So just for example, I'm going to let it be 6. The mass of baryons enclosed, that's what it was before. The mass of the halo, now I'm going to make the simplified approximation that the halo is perfectly spherical. And so I'm going to integrate over that density by integrating over different volume elements. So when I integrate over the angles, I pick up a 4 pi. And there's an r prime squared that shows up in the integration measure. And I'm going from 0 to r, right? This is telling you that I'm using the NFW profile. In any case, you go ahead and run it, and you get this, you get the curve that I just showed you. That's if you just had baryons, but then if you had a dark halo like this NFW halo, you'd find sort of agreement at small r's, but then, with this additional dark halo, you'd find that the velocity rotation curve continues to grow and then sort of flattens out. And well, it's not going to keep going forever. If I now integrate out to, let's say, r, not just of 10 scale lengths, but 100 scale lengths, eventually in this model, you'd see that indeed the curve should fall off like 1 over the square root of r. let me go ahead and go back to 10 and just show off a couple of things. If I, instead of just keep the parameters fixed, what I can do is I can imagine having some control over how strong or how much the mass there is in the halo, and I'm going to parameterize that by some little parameter A. And so what I'll do then is let that be a function of A. So let me put that here, AA. And now I'm just going to manipulate that. So we can see what happens as I adjust the amount of dark matter in this halo. So I'm manipulating AA from like 0.1 to, let's say, 1. And now run this again. If I didn't screw this up too bad. Ah, fantastic. So what you're seeing down here is right, by adding a dark halo with a small amount of mass, you do get an increase in the velocity, but not substantial. And now if I increase the dark halo, you can see that that sort of, well, it makes that curve rise, it makes the gap bigger, and it certainly makes it sort of flatten out, at least at the scales at which we look. So I can turn it on and make this bigger, bigger, bigger. Turn it down, turn it down. Why don't I go ahead and integrate again out to, um, 100 scale lengths out, and I'll show you the same thing. Eventually, at far enough distance, you expect that the velocities to fall off. But at least what you can see is that you get some, right, some flattening closer to the core, and then eventually it will eventually fall off.
So the last thing to add to this discussion is just that so that you can do problem number 4 on the assignment, is that if you think about what the mass distribution does, assuming spherical symmetry, then inside a sphere of radius r, you would write m of r is equal to right, so integral over the volume, different volume elements, and rho of, I'll write it as r prime. This integral over volume element can be written as, assuming spherical symmetry, you integrate over the over theta and phi, that gives you a 4 pi, and then what remains on the inside is an integral from 0 to r, dr prime, r prime, quantity squared, rho of r prime. And that's what that allows you to do under those assumptions, is that if you think about it, if you then take the derivative of m of r with respect to r, what that will do, oops, what that will do is basically give you, taking the derivative of an integral, if you like, the derivative undoes what the integral does. And since r only appears in the upper limit of integration, what that really does is it allows you to evaluate your integrand at that limit of integration. In other words, everything here. So what you end up with is an r squared rho of r. And so that is the sort of justification for the starting point of problem number 4 on the assignment.
What do you think, pal?